This is my final presentation on harmonic measure for Math 206 at University of California, Davis. So first, what I'm going to talk about. I'm mostly, given my time constraints, going to be focusing on the motivation for harmonic measure, defining the harmonic measure, specifically through Perron's method, and using Perron classes, or Perron, not sure how it's pronounced. And then lastly, look at some interesting facts and uses for harmonic measures. So, why is this particular measure harmonic? That comes down to thinking about harmonic functions, which harmonic functions are ones you've probably come across. They deal with the Laplacian here, and it's any twice differentiable function that satisfies this property is described to be harmonic. Harmonic functions, they're super common. They show up everywhere in PDEs. But yeah, but you also get them showing up in cases of minimal surfaces on manifolds. Those are harmonic maps. And same with conformal dynamics. You're looking at repeated iteration of conformal mapping, and a lot of that deals with these harmonic functions in the complex plane. And the last bit when talking about the harmonic measure is Dirichlet boundary conditions. Since you have the harmonic functions, it's a PDE, you have to get a sensible, unique solution. You need to specify boundary or initial conditions. In this particular case, we're looking at Dirichlet boundary conditions. So an example here is on some domain omega, when this whatever differential operator, I'm just using the Laplacian, is the differential equation, and then on the boundary of your domain, it has to conform to some function. This is important because it is one of the more ubiquitous types of boundary conditions and is quite common. And Lee shows up in cases with diffusion and heat, which are very common. So it's natural that we'd be interested in continuing and studying that. Now, getting to the harmonic measure itself, we're looking at omega as an open and bounded domain. There's more where you're dealing with unbounded domains with finite perimeter and other cases where you can look at the harmonic measure, but we'll focus mostly on the open and bounded domain case. So here we're defining the harmonic measure as the unique radon measure on the boundary, such that we have this, the h of f, which we will get to defining later. It's related to the Perron classes that gave the Perron method, how we're defining the measure, its name. And it's basically the measure that produces the desired Perron class. Perron solution for all continuous functions on the boundary. So, a little bit of the background before diving into it. Looking at subharmonic and superharmonic, functions. A function, as you can see here, is subharmonic if it's upper semi-continuous, and it is bounded by this integral, which is the integral of some compact subset of the domain that's normalized by the size of that domain. So basically, if you have a compact domain and you integrate across it and then normalize by the size, the measure of the domain, then and it's upper semi-continuous, then it is subharmonic. So you're looking for functions that are basically like sort of below themselves, hence sub. Likewise, superharmonic is the same but greater than or equal to. Now that we've introduced both the upper and lower, or the sub and superharmonic functions, we can look at defining the parent classes, which is what we use to then define the h that is used in determining in defining the harmonic measure. So I'll start with talking about the lower parent class. You're looking at all of the functions u that are continuous on the whole domain, where it's subharmonic, and the lim sup as you approach the boundary is less than or equal to the value of the function. Important thing to note, the parent class is defined for a function. So for the function x versus x squared, you're going to necessarily have different parent classes. And similarly, the upper parent class is just the superharmonic functions, but you're looking at the lim inf as you're going to the boundary. So we're dealing with a bunch of functions that are defined to be above and below the value on the boundary, so it makes sense to look at like the sup and inf for those. So we're finding cases where the function of the lim sup and lim inf are either less than or greater than the boundary function. And then we want to know basically what is the biggest function that is below the boundary function, and then what is the smallest function, what is below or what is above the boundary function. And then we can call a function resolutive if the sup of the lower parent class and the sup of the upper parent class, or the lower and upper parent solutions, are the same. And then looking for cases where this is relevant is very important when dealing with the harmonic measure. Now, with that introduction, going back to the definition, you can see that we are basically jumping back. We are finding stuff where it's bounded by some integral value on either side. So we get an integral that is interested in what happens on either side of it, and once they crush down, once you limit them together, you have this information at the boundary. And an important thing, dealing with it and thinking about it in terms of the boundary, we'll talk more about it, but one of its common uses is talking about Brownian motion and using the measure such that it tells you the probability of some random walk going through that subset. So we'll go into a bit later, but this function, we're looking at the probability that this particle following Brownian motion and traveling inside of this domain hits the boundary and leaves, which is very applicable in a lot of applied science, applied math and other notations. But the basic idea is we are defining this measure in a way that's convenient to talk about the boundaries. and how stuff like approaches and travels through the boundaries. Before or continuing on, figured I would include a small proof about like the existence and uniqueness of the harmonic measure. Since we're looking at this like bounded domain in RD, the boundary of this domain is compact. And by Rie's representation theorem, we get that the measure must be exist and is unique. Thus, as long as we show that f is resolutive, we get and show the equality of this statement, we have what we need. So that is fairly straightforward, since one of the we could go into it, but given the limited time, figured I wouldn't. You can given that the polynomials are dense in the continuous functions on the boundary, you can get a polynomial such that for a given epsilon it's arbitrarily close. And since polynomials themselves are resolutive, you can then create this following like inequality. You have the upper parent class. We always get the lower parent classes are less than or equal to the upper parent classes. That just naturally shows up by how they're defined. So we just need to show the other direction. So the upper parent class is because you have this polynomial that's arbitrarily close. It's less than or equal to the upper parent class of that polynomial plus epsilon, which, because it's resolutive, is equal. It's equal to, but that if it's equal, it's always less than or equal to the lower parent class. But then because of how close it is, it's that plus 2 epsilon. And then sending epsilon to 0, we get that they're the same. Therefore, it's unique and exists. Couple useful facts. As I mentioned earlier, it's the probability that the Brownian motion goes through the subset of the boundary that you're measuring. So it makes sense that it itself is a probability measure. As a short proof, the proof of that's quite short. You can just consider measure the total boundary, which is just the characteristic function, but then for the boundary, but then you're just looking on the boundary. So it's just 1. So we're looking at the parent class of 1. And since that's the function, looking at the definition, you're looking at functions such that their lim sup is less than or equal to 1. So the function that's just always 1 is clearly in both. Therefore, they're equal, and h of 1 is 1. And thus, since the total measure of the boundary is 1, it must be a probability measure. And then the other really neat property, when you're looking at a bounded open set that is, and there's a harmonic measure on the set omega, and you have a measurable boundary, then the function itself is a harmonic function. So the fact using the measure on a subset of the boundary itself is necessarily harmonic, which is just neat. Lastly, I want to go over a couple examples and uses for harmonic measures. One of them that I am personally fascinated by is dynamical systems in ergodic theory. When you're talking about something being ergodic, does it explore the space, which lends itself very well to the idea of harmonic measures, because you're really looking at Brownian motion, motion through the space. So it just fits very well. So you're looking at cases where like this isn't ergodic, it's not going, it doesn't have the probability of going there. It doesn't have, it's not even necessarily equal probability, it's the probability you get to a random point is equal at I'm blanking on the definition at the moment. Basically, the short version is a system is ergodic if it explores all of its space. So we've got a variety of like non-ergodic things, and then these are more ergodic. You can see that they fill and start exploring the space, and it's very important to understand like if a dynamical system is ergodic or not, because if your system can explore all of like the space or all its possible states, that's very different than if you have restricted like exploration, and you can get cases where that property will swap. And then lastly, even beyond the more like physicsy and applied stuff, you can look at stuff with like conformal mapping and conformal dynamics. So here's just some cool like mapping. The one far left is just equally spaced lines under like the particular measure. One thing to note: they're equally spaced in measure, but not in like, oh god, why am I blanking on the word? Actually, the existing space. So while they're equally spaced under that measure, you see this sort of like deviation, which relates directly to the harmonic measure and the fact that in between these boundary lines, it has equal probability going through here, through this little area, and yeah, you can the property of like the Koch snowflake here and the way that the Brownian motion would pass through the boundary or move through the boundary by the fact that it's a fractal gets sort of like spread out and distributed. How the paper that described this actually talked about that if you had a finite boundary and it's a castle, you have to guard the whole thing. But if you're dealing with a fractal, you only need to care about a measure zero and guard a measure zero subset of it. And you can see that in like these couple of examples. The areas like out in the snowflake, like out towards the edges, the motion isn't exploring that space as much as the inside or further out. And then with even more walks, you see the like white spaces in the gaps where it's harder and less likely for it to be in comparison. Here's the references for everything I had, and thank you for listening.